Well, welcome back to another big night in Algebra 2, and tonight we're going to study something called the remainder theorem. And I promise you this, it's definitely going to start off a little overwhelming. It's a slightly complicated topic, but at some point we're definitely going to have a breakthrough, whether it's the middle of this video, towards the end of the video, or maybe it won't happen until halfway through class tomorrow when we start practicing them some more. But I promise you're going to have a breakthrough, and at that point it's going to become very, very easy. But I want to start off planting the seed here by asking you, what is the connection between the remainder when a polynomial p is divided by a linear factor called x minus a? Remember, a is just some random number, so this might be x minus 2 or x minus 3. And then the value of p of a. Again, it's very complicated when it's all in letters like this, but let's dive in and look at some real numbers. So first things first, they've given us this polynomial function. It's a second degree function or a quadratic function, and they want me to divide it by a linear factor, x minus 2. So I'm going to start off with my long division here, x minus 2 into 3x squared, and I've got every term, so I didn't have to insert any placeholders or missing terms there. So go ahead and work out this long division and see if we get the same thing. So here's what my long division looked like. I worked my way through it, and then at the end of the day, I was able to make this conclusion statement. I put a little therefore symbol there at the beginning, and I said, therefore, 3x squared plus 8x minus 4 divided by x minus 2 equals 3x plus 14 with a remainder of 24 divided by the factor x minus 2. Now compare that to evaluating f of 2. So we're going to substitute a 2. And let's see what we get out of this, and go ahead and try the number crunching. And my number crunching ended up giving me a 24. So again, let's ask ourselves that question: what's the connection between dividing a polynomial by a linear factor compared to just evaluating f of 2? And you may start to see a connection, and just kind of keep that to yourself, and let's try it on the next example and see if it holds true. So again, a very similar example. They gave me a little bigger polynomial function. We're going to try to divide that by x plus 1. Again, let's see. I've got a cube, I've got a squared, I've got a linear, and then I got a constant. Okay, go ahead and perform your long division. So here's what my long division looks like. So I said, therefore, if you take the polynomial x cubed minus 3x squared plus 6x plus 8, and if you divide it by the linear factor x plus 1, you get a quotient of x squared minus 4x plus 10 with a remainder of negative 2 over that factor x plus 1. Now let's go ahead and compare that to g of negative 1. So I'm going to go ahead and substitute, and let's see if our number crunching is the same. And let's see, my number crunching ended up giving me, let's see, negative 10 plus 2, negative 2. So again, we're looking for a connection between performing our division versus just evaluating g of negative 1. And again, see if you see any connection here compared to here. Let's take one more shot at this. Let's go ahead, and our long division setup is going to look like this. Now watch out for this bear trap. I'm going to put a 0x squared in here, and then I'm going to go ahead and work it out. So my long division worked out like this with a remainder of 30, so I can say, therefore, if you take the polynomial x cubed plus 2x minus 3, and if you divide them by the linear factor x minus 3, you'll get a quotient of x squared plus 3x plus 11 plus a remainder of 30 divided by the linear factor x minus 3. Let's go ahead, and this is our last time through, but we'll evaluate h of 3 and see how the result compares to the quotient that I just got. Haha, very interesting. In fact, maybe you even saw this number coming once you saw this rascal right here. You were starting to predict that you would have gotten a 30 over here. So I think we're starting, after 3 examples, we're hopefully starting to see a connection or a little pattern involved here, and hopefully we're gonna try to generalize this connection into the remainder theorem and then use it as a major shortcut as we work out some future problems. So what I did here is I imported the 3 examples we just worked out, and also the original question that we opened up tonight's video with. So when we said a random polynomial p, we were referring to functions like f of x, g of x, and h of x that you just saw in the last 3 slides. We're dividing them by a linear factor x minus a, which was, we saw x minus 2, we saw an x plus 1, we saw an x minus 3. And I want to compare these quotients that we're getting to the value of p of a. Notice if our linear factor is x minus 2, we're evaluating f of 2, not f of negative 2. If my linear factor was x plus 1, I'm evaluating g of negative 1. And if my linear factor was x minus 3, I'm evaluating h of 3. And the color-codedness shows us that this remainder matches the value of f of 2, or this remainder matches the value of g of negative 1. And of course, this remainder matches the value of g of 3. So how in the world are we going to generalize that? Well, we call this the remainder theorem. And here's what this rascal says. He says for a polynomial p of x, the value of p of c, which corresponds to like our h of 3, that's going to equal the remainder when p of x is divided by who? X minus c, the linear factor x minus c. And that's what the remainder theorem says. It says he guarantees that they're equal to each other. So what's the big whoop, right? Big whoop. What's the big deal about this remainder theorem? Well, what it is it's a major shortcut. It's going to save us a lot of time. And here's why. Imagine, go back to those 3 examples we did earlier, and imagine yourself being able to skip all that long division. Tonight they're going to ask me, what's the remainder when f of x is divided by x minus 2? And instead of doing all the long division, we're just going to evaluate f of 2. Or check out this example here. They want to say, they're asking me what's the remainder when I perform the following long division. Well, I'm not going to actually do the long division. Here's what long division would look like. Here's the setup for it. But guess what? I'm saying that we could skip all that work tonight. And all you have to do is evaluate f of 5. And that would be the same thing. And f refers to this function right here. And I'm going to substitute a 5 plus 4 times 5 minus a 2. And I got 25 plus 20 minus a 2. And I got 43 as my remainder. And that's all the work we have to do tonight. Of course, you could do the long division, but you'd end up getting the same answer. Here's another really similar question. At the end of the day, they want to know what the remainder is. So we could set it up. And again, if you're madly in love and you just get really excited doing long division, then go for it. Knock yourself out. But I'm going to say I'm just going to evaluate f of 2. And let's see here. By the time I get a 4 minus a 12 plus a 2, I got a negative 6. And ladies and gentlemen, that's my remainder. I'm done already. These questions are going to take us about 30 seconds apiece. Well, starting with this slide, in the next couple of slides, the wording has changed, the phrasing has changed, the terminology has changed, but at the end of the day, the same concept pervades and or persists, I should probably say. So they said, here's this ratio. Well, really, all a ratio means is we're dividing, right? So let's say, here's my f of x, and I'm dividing him by the linear factor x plus 5. That would be equivalent to saying something like this. You're probably more comfortable with writing it like this, perhaps. And they said, hey, we're going to place it in this form right here. Well, guess what? All you need to know is that r represents the remainder, okay? So just keep telling yourself, little r represents the remainder. And so they said, of course, q of x is a polynomial. What's the value of r? Same question as we saw in the last 2 examples. What's the remainder? And instead of doing all this long division, I'm just going to evaluate f of negative 5, okay? And f is referring to this function right here, so I'm going to go 2 negative 5 squared. And of course, I get a little nervous when it's a negative 5 instead of a positive 5. Oh, goodness gracious, I'm squeezing in my plus 13 there. So when I evaluate this, make sure you're doing negative 5 squared, which is 25, then multiply by 2 to get your 50, minus 60 plus 13. And I got a final answer of 3. So I've got a remainder of 3, or we could say r equals 3. Again, same question, just worded a lot differently. And they said we started with this mysterious polynomial p of x, and it's divided by a linear factor of x minus 6. So we're saying x minus 6 divided into somebody. We'll call it p of x for now. They got a result, or I'd like to say quotient of x squared minus 2x plus 41. 41 is your remainder. Or compare that to the last example, that would be equivalent to your little r. Okay? So what's the value of p of 6? Guess what? We don't even have to do any work. You automatically know that p of 6 is equal to 41 because that's the remainder. And so all it is just kind of recognizing their terminology and what everything means. And it's if you can find the remainder, you got your answer and you're done. This is probably the most challenging one of the night. They're saying our long division setup would look like this. We'd have x cubed plus 0x squared minus kx plus 6, and you'd work your way through it, and they're saying the remainder is guaranteed to be a 10, which in this case means f of negative 3 is guaranteed to equal 10. So what we're going to do, they're saying if we plug a negative 3 into this function right here, we guarantee the answer is going to be 10. So we could do that and solve for k. So I'm thinking negative 3 cubed, and I'm not even going to worry about the x squared, of course, minus k times negative 3 plus 6 is guaranteed to equal 10. So we got negative 27 plus 3k plus 6 equals 10. Let's see, combine like terms on the left side, and I got negative 21. Add over the 21, and then divide by 3, and I got k equals 7. But it all starts with this idea of saying, if the remainder is going to be 10, then I know for sure that f of negative 3 equals 10. Okay, the real big special thing here is we're going to review the connection between what a factor is and its connection to a 0 or an x-intercept. If we said that x minus 2 is a factor of some polynomial p of x, then what we know for sure is that p of positive 2 has to equal 0. Okay? In other words, x equals 2 is an x-intercept. If x plus 5 was a factor, then I know p of negative 5 has to equal 0. In other words, there's no remainder. Okay? Let's put that in our notebook. There's no remainder. If x minus 8 was a factor, then I know p of 8 has to equal 0. Or let's flip that whole equation around. If p of 3 equals 0, then I know that x minus 3 is a factor. If p of negative 4 equals 0, then I know x what? Plus 4 is a factor. Or if p of 10 equals 0, then I know x minus 10 equals 0. And the theme here is that the remainder is 0 or it doesn't exist. So here's a really, really wild question. First of all, just consider this polynomial. It's a third-degree polynomial, and notice there's this mysterious coefficient here attached to the x squared. They said, can you find the value of k so that x plus 1 is a factor of p? So let's focus, let's zoom in on this word. What are they trying to tell me when they said factor? What they're trying to tell me is that p of negative 1 equals 0. Therefore, if I substitute a negative 1 into all of these x's, what I can then do is set the equation equal to 0 and then solve for, yep, you nailed it, k. So let's go ahead and we'll substitute our negative 1 and see if we can solve for this mysterious value of k in the process here. So I've got a negative 1 plus k minus 1 plus 6 equals 0. Now, do you agree with all those values? Of course, when I cubed it, I got negative 1. But then when I squared it, I got positive 1. Positive 1 times k is positive k. So if I combine my like terms, like a negative 1 plus a negative 1 plus a 6, that's going to equal positive 4. And if I just subtract the 4 over, k equals negative 4. Now, how about this? Can you find the other two factors of p? This is by far the most challenging part in the video, I think. So what we're going to do first is, now that we know that x plus 1 is a factor, we're going to perform our long division to see what the quotient is when this p of x is divided by x plus 1. So let's perform our long division, and that'll get the party started. So in an attempt to find the other two factors, I used the value of k that I got. So you can see how I inserted the negative 4 for k. And I'm going to go ahead and perform my long division. And just like we did earlier in the video, go ahead and work that out really quick, and we'll see if we got the same thing. So my long division turned out really nice. And notice I got a remainder of 0. And that was no accident. And we knew we should get a remainder of 0 because we'd already said that x plus 1 was a factor of the polynomial p of x. So here's what we're saying. We're saying that p of x is really equal to x plus 1 times x squared minus 5x plus 6, which can be factored. Notice how the x squared minus 5x plus 6 can be factored into the product of two binomials. and it works out really nice, so it's x minus 3 and x minus 2. And if we had time, we could go through our distributive property and multiply all three together to verify that it does indeed equal x cubed minus 4x squared plus x plus 6. And again, the key word here is that these are what? Equivalent. Well, the good news is I think we got the real big bears out of the way for tonight, and these last couple of slides are going to be a little bit easier, and it's just going to give us more practice. So the first question, we've got this gigantic polynomial. It's a fourth degree polynomial. And their first question is 1 a zero of the polynomial p? Well, if that was true, then we know that p of 1 would equal 0. So let's go ahead and we'll substitute a 1 and see if the answer is 0 or not. And so I got 1 to the 4th plus 3 times 1 cubed minus 28 times 1 squared. They really did give me a nice number to work with. It could be worse. They could be, I could be substituting like a 7 or something. Goodness gracious. So I got a 1 plus a 3 minus a 28 minus a 36 plus a 144. And I may call on my calculator for a little assistance here. And I ended up getting 84 when I combined all my like terms. Now notice that's not equal to 0. So I said no, 1 is not a 0 of p because p of 1 did not equal 0. Okay, now for part B, is x plus 3 one of the factors? Now again, they're just testing us on can we interpret what the word factors means. If this was true, then p of negative 3 would equal 0. So let's go ahead and test that out by substituting similarly to what we just did. And goodness gracious, I am really going to use my calculator on this one. I'm not even going to try to show off or anything. We're just going to wave the white flag and start plugging it in on the calculator. And as I'm plugging that in, I do indeed get 0. So I'm thinking, yes, x plus 3 is a factor of p of x. Alright, we're cruising. Now related to that, we went ahead and we graphed function p. And just to save some time, I sketched it here off to the right. And as I'm tracing the function, it's going to cross the x-axis at negative 6. Then it's going to cross again at negative 3. It's going to cross again at 2, and then it's going to cross again at 4. So those values represent my zeros. Zeros, negative 6, negative 3, positive 2, positive 4. I'll tell you what, the questions don't get much friendlier than that, huh? Now they said, can you write an equation for p that's in factored form? And it's all based on knowing who the zeros are and the connection between a zero and a factor. So I said p of x is going to be x plus 6, corresponding to the minus 6. And then it's going to be x plus 3, going to be x minus 2, and it's going to be x minus 4. And if we had time, we could use the distributive property to multiply all of these functions out, and the answer would again agree with the original function that we started the problem with. Okay, last slide for the night, and what they've got here is they're giving us a graph of a fifth degree polynomial function that has x-intercepts of negative 4, negative 2, 1, 3, and 5. And you'll notice negative 4, negative 2, 1, 3, and 5 all show up. And we do notice that the leading coefficient must be a positive number because the graph is starting low and finishing high. And just a real nice smooth polynomial curve that crosses the x-axis 5 times. The challenge here is, can you write an equation, or in this case they use the word formula, for a possible, interesting choice of words there, huh? For a possible polynomial function that the graph represents using c as a constant factor. What the heck is this value c that they're referring to? I also like to call it a stretch factor. Because, for instance, if I wrote that f of x equals x plus 4, x plus 2, x minus 1, x minus 3, and x minus 5, I'd be partially correct. What I don't know is how tall or how low these relative maxes and mins are. Okay, so what I'm going to do is I'm going to put a stretch factor or a coefficient of c right here to take into account that I'm not sure what the heights are. I know what the x-intercepts are, but I don't know what the heights are and stuff. So I'm going to put in a value of c, and watch how this plays a role in the next question. Suppose that we knew the y-intercept had to be -3. Can you adjust our function so that the y-intercept yeah, let me start over. Can we adjust our function to fit the y-intercept by finding the constant value of c? Well, what we know, when we said that the y-intercept was going to be -3, what we're really saying is that f of 0 has to equal -3. So I'm going to go ahead and I'm going to substitute a 0 for each of these x's, and I'm going to set the equation equal to -3. And by the time I do that, I can solve for c. So check it out. This is what it might look like. c times 0 plus 4 times the quantity 0 plus 2 times the quantity 0 minus 1 times the quantity 0 minus 3 and times the quantity 0 minus 5, and the product has to equal -3. So we've got 0 times 4 times 2 times -1 times -3 times -5, and let's see, is by the time I multiplied the 4, 2, -1, -3, and -5, I got -120 times c equals -3. And I'm going to divide both sides by -120. And that gives me c equals positive 1 over 40. Very interesting number. So if I put it all together now, I could say that this function that was shown in that graph is 1/40 times all of these factors. And if we plugged this all into the calculator, then by golly, the calculator would show us the exact same picture we had up at the top of our screen right here. So again, we're going to get a lot of good practice with the remainder theorem tomorrow, and there's going to be a lot of shortcuts. We won't have to do too much work tomorrow. Most of the problems are going to be 30 seconds or less, just being able to identify who the remainder is, and then we're off and running. All right, good luck. We'll catch you tomorrow.